Hi, everyone. Thank you for attending Javelin's virtual tech conference for 2020. My name is Janateas. I'm the manager of the professional services group in the additive manufacturing department at Javelin. And today we're going to be discussing optimized manufacturing aids using the advanced FDM features within GrabCAD Print. Before we get into it, I just want to overview what our department does here within Javelin. So as the professional services group within the additive manufacturing group, we support our customers, both machine customers and non-machine customers, with a number of services. Direct digital manufacturing is one of the services that we specialize in, whether it's advanced prototyping, tooling and manufacturing aids, or a turnkey production run. We're able to assist with all. We can take on work from outside firms as well as support our existing machine customers with overflow production capacity. And we're also able to provide design and product development services. So this goes hand in hand with our direct digital manufacturing, and it's what allows us to enable product development from the initial onset complete through to either functional prototyping, final prototyping, or if we're shooting for production with additive, all the way to production. And of course, we also specialize in design for additive manufacturing as well. So taking an existing part and optimizing it for additive. And again, we do that as a service for existing customers as well as new customers. We also provide 3D scanning, reverse engineering, and metrology services, typically a part of our design and product development, but also just as its own standalone service. And we also provide consultation and applications development services. So whether you're looking to implement a new piece of 3D printing technology in-house or looking to use one of your Stratasys machines for a new application that you haven't quite tested out yet, my team is available and here to help when developing those new applications. Okay, so we're going to start by overviewing the current print prep process for Stratasys FDM machines, and then get into some of the common problems that are plaguing this workflow. So just to orient ourselves, we have two different ways of prepping files for FDM printing on Stratasys machines. We can use GrabCAD Print or Insight. We've highlighted some of the differences here between the two. The most important one really, and the biggest distinction, is that GrabCAD Print works directly with your CAD file. So you can go straight from any CAD environment, whether it's SolidWorks or Autodesk, bring it into GrabCAD Print and directly start working on your parts and preparing them for print. Of course, Insight, we're working with STLs only, and there's another step in file conversion there. GrabCAD Print also has integrated file repair, and it's quite comprehensive. From my experience, it does a great job for 95% of the issues that typically would plague an STL or even a CAD model. My rule of thumb is always, if the GrabCAD Print repair feature can't fix it, then it's likely going to require a relook at the CAD files itself. We can also do batch processing with GrabCAD Print, bring a number of parts in and apply the same parameters to all of them at once, whereas with Insight, we're working file by file. GrabCAD Print works with all the Stratasys FDM systems, and it provides you more of a high-level approach to prepping your file. So slider-based versus value-based, whereas Insight gives you more granular parameter control, lets you adjust a lot more features overall for the build as well as a given layer, and also lets you leverage custom slice groups as well. Insight is only available on the F900, the 450, 380, and the 370. So traditionally, what we do is we slice and then we modify our build parameters, and we get our control from custom groups. But in this instance, we're limited to per layer control for a given contour set or a given custom group. And so we want to see, how do we overcome that? And typically and traditionally, the way we've overcome that is by using multiple slice bodies and then combining them with custom groups. So on the left here, we have an example of a comprehensive pulp and paper tool that's been done using a number of different STL files that have been processed independently and then combined within Insight in order to give us different interior fill and different parameters for different groups. Now, it's a pretty comprehensive process. Of course, it requires the correct design within CAD, but it does take a lot of time to prep these files. There's CAD work and Insight work. It is orientation dependent, so if we get to a certain point and decide, oh, I actually want to orient this differently, it changes not just the custom groups that we're working on in Insight, but it changes the entire CAD process that we have to do. So we have to go back and start from scratch. It also is pretty prone to user error. Typically for a file like this, it involves going through every layer once they've all been combined and making sure there's no overlaps, no erroneous offsets or anything like that, in order to ensure that the part you are looking to print actually comes off the way you've intended it to. The other problem really is we end up compromising. So rather than spending a lot of time, doing all these different custom groups and everything like that, we'll typically just print it as solid. And of course, that's not optimal from a production standpoint, both with respect to material consumption as well as print time. We also have to take a look at the prep time, right? Again, we'll typically go full solid and just get it on the printer so we're not wasting time going through this complex multiple group workflow. So even though this CAD feature within CAD has multiple bodies, multiple faces, a lot of different features, when we bring it into Insight as just one STL with a number of triangles. And again, we're limited to processing layer by layer, slice by slice. So, typical options, we'd go with solid. Of course, that's going to give us the highest strength, but it's also going to take the longest and cost the most to print. We could also look at doing a sparse infill. Again, applying this globally, it'll be less material, less time to print, but may not provide adequate strength. Of course, we can adjust the layer parameters on a given set of layers, but as mentioned previously, those parameters apply to the whole layer. So if we're only looking to optimize one little section of a part, unfortunately, it means we're optimizing or adjusting the layer parameters for that whole layer just for a specific area of said layer. To address the strength concern, of course, we can look at doing hexagonal. It's a fairly common infill type when print time is not of the essence, but of course, with the hex infill, it requires a lot more head moves for a given layer when compared to sparse or even solid. And so the print time, even though we're printing with less material, typically is higher than that of a solid part, or in and around the same time as a solid part. And again, we're not able to optimize specific areas of a given part. We have to do this globally. And this brings us to highlighting the advanced FDM feature set within GrabCAD Print. We'll look at all the different features and what it enables, and then we'll get into a practical example with some advanced fixture design. So as mentioned, in advanced FDM, you can work with CAD features. So GrabCAD Print enables us to work with CAD, and because we're able to do this, when we're in advanced FDM, it can recognize particular features of CAD, whether it's a body, a face, a hole, a fillet, and then we can apply specific parameters to those features rather than globally to a layer that contains said feature. It also allows us to work with multi-body CAD assemblies. So if we have a number of different bodies embedded in an overall product, we're able to apply specific infill styles and parameters to specific bodies in that CAD, yet still print it as one piece. And this all happens directly during the print prep. So unlike Insight, where if we want to do some of these advanced workflows or features, we have to pop back into CAD and readjust everything and then pop forward and go back and forth, we can apply this stuff directly when we're prepping the print. And what it allows us to do is, obviously we can reinforce bodies and we can also selectively reinforce faces. Allows us to adjust holes. We can make them self-supporting, or we can automatically size them for inserts. And then of course we can also avoid seams. So if there's a particular surface that's of utmost importance, we can tell the machine to avoid printing seams on that layer and on that face. So just to compare the two, on the left is what we typically see in Insight. Again, one STL, number of different triangles. On the right, this is how we view the part in GrabCAD Print. So views it as a CAD body. You can, of course, select CAD faces, CAD circles, and use fillets to help reinforce the part. So again, one CAD file with feature-based adjustments. And so this is an example of some of the areas on this part that we may want to adjust. So we can see it's a CAD file, and I've added some transparency here just so we can have a view of the reinforcing bar that goes throughout the part. So in this sense, we'd have at least two bodies, the main body plus the reinforcement body, and then we can again apply custom parameters to both of those bodies. As highlighted here, you can see the different areas where we may apply some of the different features, whether it's different infill styles, self-supporting or insert-ready holes, or reinforcing faces. And so we get into this when we're looking at multi-body infill. On the right, we see what the menu in GrabCAD Print looks like, and we'll hop out for a live demo so we can see exactly where this lies within the software. But you can see it's a very simplified way of adjusting different parameters. So we can pop in there, select that pink CAD body, and then say it's a stiffening rod, apply solid infill style, which we see on the right here. And then again, we can even adjust some of the other parameters. So body thickness, how thick the shell is, infill angle, and then we can tell the printer to use thick and thin walls or variable width remnant fill. If we look at face reinforcement, same thing. So we can select a particular face or number of faces at once and apply a specific thickness to it, as we can see on the left. Now you'll notice up in the model settings, we've switched over from body selection to face selection. And this is what allows us to select a face and apply specific thicknesses, as well as tell the printer to avoid seams on the given surface. And finally, when we're getting to holes, of course, we can do a number of things, as I've already mentioned, apply inserts, make them self-supporting, and avoid seams. And this is done by selecting a cylindrical face within the CAD model. So we just have a quick overview, live view here of what this looks like. Just a quick note, this is a previous version of Advanced FDM, so the menu on the right is slightly different than what it is in the latest release, and we'll get a viewpoint of that in the live demo. But we're overviewing what we can do here. So we've just selectively reinforced a face, and now we can see in the slice preview, when we go in and zoom in on that region, you can see how reinforced that area on the part is. Now for an example with holes, so we're gonna select these 4 holes here, and we wanna make them self-supporting. So we click the checkbox, update the model geometry, and we can see the CAD change that's occurred directly here. So typically we have to pop back into our CAD suite, make those holes diamond shaped. Again, it's orientation dependent, and pop back. Finally, we can see our reinforcement of the part with the reinforcing bar. So you can see that globally the part is sparse, but then in that reinforcement bar, we have a solid infill there. We've adjusted it for strength, and we've made it solid. So that's just a quick overview of Advanced FDM in GrabCAD Print. Now, that is applicable for all the Stratasys Fortis machines, all of the F-Series machines, except for the Stratasys F120. So if you're running an F170 and upwards, this workflow is applicable for you. And now we're gonna hop into a more relevant example about how we can leverage advanced FDM within GrabCAD Print during part design process in order to optimize our outputs. This is an actual example of a fixture that we're using to polish some parts in-house. So this is a prototype tail light. Of course, when we're printing with PolyJet, we need to typically do some polishing if we want glossy surfaces and transparencies. And so we went through and designed a fixture in order to optimize this process, this polishing process in-house. So fixture 1, here's an example on the left. We can see very blocky, clearly designed for subtractive processes. It's not ergonomic. We have difficulty accessing the part for polishing. It's typically table mounted, so operators can't hold it very well in their lap and continue polishing, so it's less ergonomic. And it's also hollowed on the back, so it ups the print time, even though we're saving a little bit of material consumption here. So what we get into is going through design for additive manufacturing, and we've done a number of things here to optimize this fixture. So of course we've retained the same mounting point, but now here we're looking at having a wider base so there's more area to hold. Of course, we've removed all the superfluous material and just left this shelled out. And we've removed the cap layers, both on the cap of the handle as well as the top of the fixture. That way we're not printing support all the way up into the handle and into the bottom of this part. So we're saving even more material consumption there. Now, depending on a user's experience with FDM, we may look to print this and just validate it, verify shape. For those who are more experienced in design, it'd be a quick look to say, yep, this is gonna be an improvement. Of course, we've addressed the access to the part for polishing. It's a lot more ergonomic now. It's a wider base, so we can look at having a user hold it on their lap for polishing, etc. But we want to evaluate and optimize this thing further. So at this point, a lot of people would just jump off, print it solid, and call it a day. But we want to see what's really going to go on with this part. So when we're doing that, before we're even printing, we can look at where this part may have some stress and may need some more reinforcement. And so we can see we've highlighted all of the features here: cut-off roof handle, the cutouts, ease of access, and grip points. Now, when we run this through FEA analysis and the flex that's likely going to go under as we're starting to polish, we can see that the part has some flex. This is assuming 100% density, so we know that if we're going to print this in a sparse infill or sparse double dense, the potential force and the potential for flexion in the part is going to be even more substantial. And so we can see here in the parts that are highlighted in the green and into red areas while it's flexing, that if we print this in full sparse, we're likely going to need some adjustments and some improvements. And that's where we'll look at leveraging advanced FDM and some of the capabilities that it provides to optimize this part even further. So what we want to do to prepare for advanced FDM, we want to work with that multi-CAD body workflow. So what we can do is apply stiffening rods to the part, as well as know that we're going to want to reinforce all of the filleted areas and make sure that any area on the part that we want to reinforce has an applicable face or fillet to reinforce. So we can highlight here in the pink, we have these reinforcement bodies that would be printed in solid. And then we can also see all of the orange fillets that we would be looking to reinforce within GrabCAD Print when we're printing or prepping the print. So now we're just going to hop out of the presentation and into GrabCAD Print for a live demo. And here we are in the GrabCAD Print software. We've selected the 450 MC. Again, this is applicable for everything F170 and up. And I've gone ahead and already loaded in our files here. We're showing everything. So we have the actual part that we're looking to polish. So we can go ahead and hide that. And then we can see we have the stiffening bar. We have the stiffening bar, and the rest of our optimized design here. So if we were to say go ahead and assemble these right away, we're not able to leverage the multi-body workflow, and it'll go ahead and apply those default parameters for all of the bodies within this. That's just the standard way that the GrabCAD Print works, and that's just to ensure that there's no erroneous parameters applied if we're working with multi-body parts where we want everything to be the same parameters. But in this instance, we don't. So what we're going to do is we're going to go ahead and group these parts. Actually, I'm going to go ahead, we're going to group all of the parts, and you'll notice the actual tail light pops back up. So we want to make sure that is hidden again. You'll also notice that the original CAD that we've imported has been hidden, and now we're working with a specific custom group here. And what this means is that when we disassemble and apply specific parameters, ultimately those parameters will be retained even when we go ahead and reassemble this CAD file. And one thing to note, just because we haven't seen the import process here, we can see up in the file name, that's just a step file. So that's been pulled directly from my computer. It can also be sent directly from SolidWorks. No additional processes required, and we can see that we've retained all of the bodies and all the features of the CAD when we've brought it into GrabCAD Print. Okay. So in the most recent update of GrabCAD Print, they've also moved all of the advanced FDM settings within the general print prep. So previously, it would be a separate module that you'd hop in to prepare everything and send over to GrabCAD Print. Now it's all embedded in the same workflow, so you can work on parts with advanced FDM and parts just with regular processing all on the same tray, which makes things much easier and more efficient. So let's go ahead and apply some specific parameters here. So we're going to select the reinforcement bars and already solid. So we're going to make those solid. Let's go ahead and move over to the face selection tool and reinforce some faces. So we can see some that have already been previously selected. They're highlighted in green, and we can see that we've wanted to reinforce those features 0.2 of an inch. Now, of course, if your GrabCAD's in metric, you'll see those values in metric. I'm going to go ahead and selectively reinforce a few more faces here just so we can see what this process looks like. We can see that we've selected a new surface, and so that surface thickness has been decreased back to the default. I'm going to go ahead and make this, let's call it 80 thou. So just under what we're doing for the rest of the fillets, a little less reinforcement, and I'm also going to say avoid seams. Now, this is a cylinder, so you're not going to be able to avoid seams everywhere. But if I had selected 3 of the 4 faces, then we'd see some faces or some seams being avoided there. Again, here, I'm going to selectively reinforce this to 0.1 of an inch. We can also go ahead and override and just type right in. And again, we see that retained in green. Now, if I go to the body selection tool and select this body, it's also solid, and we don't want that. So I'm going to go ahead and select sparse infill. We can go ahead and decrease the infill density. I'm going to go as low as possible, 14%. Now, these parameters have been validated by Stratasys, so you're fairly safe to go and dump that down right to the smallest value or the smallest infill density. Body thickness, this is the contour, or the number of contours around for those Insight users that are familiar with that terminology. It can be adjusted. Right now we're at the default body thickness, which is an outer contour plus 2 inner contours, so 60 total. Again, we can thicken that up if we want to, but because we've selectively reinforced all of these faces, there's no need to globally go ahead and reinforce the rest. There's no holes on this part where we'd want to make self-supporting or apply an insert, so we're not going to see that selected or performed here, but it is another powerful feature within the software. Just to give a quick example, so if I go ahead and select this face, if I want to apply an insert here, I could theoretically go ahead and apply an insert. Now we see a warning, model geometry is out of date. What this means is I haven't updated the model geometry based on the insert that we want to put in here. Of course, we wouldn't actually be putting an insert because this is where the light goes, but for the purposes of this exercise, it exemplifies what we'd want to do. So we can choose a number of different inserts, heat set, helical, or a custom where we input our own dimensions. So I'm going to choose standard, just choose any old insert here. I'll make it short. We're not needing to avoid seams. Now I'll go ahead and click update, and we can see my geometry has been updated on the fly to account for that insert. So that hole is automatically sized properly. We can take this part straight off of the printer and plug those inserts right in. I'm going to go ahead and remove that insert application, update the geometry, and we can see it's reverted right back to normal. So this is what we use in the shop if we have CAD files and we're adjusting insert types on the fly based on what we have in stock or what the customer wants. Rather than pushing the CAD work back to the customer to have them update it, we'll simply just update the insert type and go ahead and print. Now that we've adjusted all the different parameters, we're going to go ahead and assemble this and then do a quick slice preview. And this will show us, we're slicing here on the fly, and this will show us all the different parameters that we've adjusted on the file here. Okay, so now that we're finished slicing, we'll start at the top and work our way down. So we can see we're solid, 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 and now we're starting to get into where we've made some adjustments. So we can see the sparse around here with that 100 thou surface reinforcement that we've done. Go down further to the main body, and we can see here again, so we've gone ahead and reinforced this inner surface, 200 thou, and we can see how we've optimized that there. It still retained the sparseness on the outside. And we scroll down even further, again, we can see where that reinforcement has stopped. And now we're in the part and we can see how complex we've gone. So you can see the two stiffening beams on the top and the bottom, as well as the I-beam here. And then you can also see the 200 thou reinforcement that we've done on all of these fillets. So by providing a solid infill here on all of these fillets, it adds strength to the part, helps us prevent flex around these points, and ultimately will lead to a stronger part. Now we'll pop back into the presentation and continue on from there. Okay, so this is what the printed version will look like once we have gone ahead and sent that off to the printer. We can see how the reinforcement is translated into real life value. So again, 200 thou reinforcement here, as well as stiffening bars. Now, we could leave this fixture as is and call it a day here, but we know our guys in the shop are going to be using and abusing this, and we want it to be as strong as possible, as stiff as possible, and have the best longevity. So we have a number of these to go through and polish. And so we've come to the final version of the fixture where we've updated the material. So that green prototype on the last slide is ASA, cheap, great for prototyping. But we want to move to something a little bit more robust for the production part, and that's where we'll move to our nylon 12CF. Stiff, durable material, long carbon strands, 33% carbon infill, very stiff, very strong, and we see superior performance compared to some of the other carbon infill options out there, specifically the powder-based carbon materials. Of course, some of the other things that we've addressed during DFAM, optimizing the part for additive, making it more ergonomic, portable, and improving part access has all been retained in this final form. And to give you an idea of what the part looks like when it's fully been completed and printed, here we go. And so by leveraging the advanced FDM feature within GrabCAD Print, it allows for a much more agile design cycle because you're able to do some modifications and some adjustments directly within the CAD software, or within GrabCAD Print, pardon me, and avoid moving back to the CAD software. So if we look, we can go from original shape, DFAM, and advanced FDM all within a single step. Even if we wanted to look at doing some stiffening rods, of course, we'd have to jump back to CAD for that particular aspect of it, but all the other features and things that we've adjusted would be encapsulated right in advanced FDM without having to jump back to adjusting our DFAM further. And again, those that are more experienced with additive would likely be thinking ahead, okay, I'm likely going to print the solid, want to save on materials. Once I get my near net shape, let me do an FEA analysis and see where I'll need some reinforcement bars, put that into the CAD and the original design phase, and then pop straight into advanced FDM. And furthermore, for those of us that use the printers often, we're quite well versed with the different material selections that are available. So you may want to just jump directly to that nylon 12CF first pass and avoid unnecessary prints. Here we always like to do a test fixture just to make sure everything is nuts and bolts and ready to go before we commit to the production part, but you could very easily do this all in one go and quite easily turn around and update an optimized fixture within 24 hours or so. So we're going to hop into a customer story and exemplify how our services and our professional services group can assist our customers and assist you with this kind of process. So we're going to look at an FDM batch placement fixture that we did for a customer of ours. This is for an automotive OEM that we've worked with over the last 10 or so years on various projects. They have our machinery in-house, but this particular tool is going to be too big for their production, and they also didn't have the design resources to take it on. Essentially what we're looking at doing is creating an optimized badge placement fixture so that they could rebadge a number of vehicles that came off the lot, or off the line, pardon me, erroneously badged. For this project, we did end-to-end project management, complete design, reverse engineering, CAD work, and production, hardware installation, delivered to the customer. And this was a turnkey product that was put right from our hands into the customer's hands and onto the assembly line. And we did this all within 2 weeks while taking on some other projects. So very rapid turnaround for a problem that was causing line stoppages for the customer. And they were quite pleased with the results. We also enabled them to use their own machine for in-house updates. So some of the smaller components, some of the different accessories that we could consolidate into one, we left separate so that the customer could go ahead and update the jig based on updated vehicles as well. And key features of this fixture. So we selected ASA material. It was strong enough, it was stiff enough, it gave the performance we need, and it also was appropriately colored for the shop floor. The customer specifically requested that the tool has to be yellow. We were also able to leverage, a little difficult to see down in these bottom corners here, we have our alignment features for in the door gaps. Those were nylon 12CF just to afford the utmost strength and stiffness, so we didn't see any flex in this tool. We, of course, have optimized this for hardware installation. So we have handle inserts, peg inserts, suction cups with proper mounts, as well as the hardware that was embedded into this part to allow for these placement, these black locating features to be added on afterwards. And then we optimized this with advanced FDM. So we had the net CAD nearly done. We knew that we wanted to do a couple things to optimize it for print, but we didn't want to go back and reopen the CAD simply because we didn't have the time in the project. So when we went to print this, any hole where we had these inserts put in, we went and automatically resized it using the hardware insert tool. We also went ahead and made some of the holes that we couldn't use that tool for, we made those self-supporting so that they could be quickly drilled out post-print and the hardware installed, but so that we're not wasting time on the printer by printing support structures. Most notably, these pegs up on the top, they would have had support generated for the duration of the build. So by switching these to self-supporting, we saved a lot of time. On the flip side of this part, so of course this isn't the vehicle side. On the vehicle side, we wanted to avoid seams and we wanted to reinforce the part so that we wouldn't see any wear through to the sparse aspects of this. So we went ahead and did the face reinforcement tool that we've exemplified previously, and in that same selection also went ahead and told the GrabCAD Print to avoid any seams there. So that was some of the ways that we've optimized this part for additive manufacturing with GrabCAD Print Advanced FDM, and it also highlights the level of work that our team is able to do here within the professional services group. And so thank you for your time. Thank you for watching. I hope this has been useful for everyone attending. Just to reiterate, the professional services group here at Javelin and the additive department, we can do direct digital manufacturing, design and product development, 3D scanning, reverse engineering, and metrology, as well as application development and consultation. Please stay tuned to our blog, as you'll see in the coming weeks and months, a follow-up series to this where we get a little bit more granular with some of the features found within GrabCAD Print Advanced FDM. So I thank you for your time. I hope you found this insightful and enjoy the rest of the virtual tech conference.